Please take a moment and watch this 21-second video. Be sure to pay attention to what happens inside the beaker. Today we're going to take a look at precipitation reactions. You have seen precipitation reactions throughout this school year when we're looking for a precipitate. It's one way for us to understand that a chemical reaction has taken place, just like you saw in the video on the first slide. A precipitation reaction is when two aqueous solutions come together and get mixed and result in a precipitate. In order for us to understand how that occurs, we have to first understand that ionic compounds dissociate when they are dissolved in water, meaning that aqueous solutions result in the dissociation of ions that make up that ionic compound. So basically, water gets in between the ions that are being held together because they're opposite charges. And now these ions freely float among the water molecules. These separated ions are what we call strong electrolytes. You may have heard about that when you see commercials for sports drinks. Strong electrolytes are what our bodies need to help us stay hydrated. We need this. Precipitation reactions are a special form of double displacement or double replacement reactions. When we learned about double displacement reactions, we learned that the anions switch. So how do we predict which product is going to be the precipitate? How do we know? We know because scientists have created a list of solubility rules. Let's take a look at an example here. Here we have potassium chromate and barium nitrate from the video on the first slide. And we need to know what is produced. You know you saw a yellow precipitate form, but yet there was still clear liquid surrounding it. So one of the products is going to be the precipitate, the other is going to be aqueous in solution. We have to figure that out. Now, when we learned double replacement reactions, we learned that the two anions are going to switch. And we also learned that we have to rebalance our ions in order to form neutral compounds as products. So let's take a look at this. If we know that the nitrate is going to come and hook up with the potassium, we know that potassium is a +1 charge and nitrate is a -1 charge. So we can safely write down a formula of potassium nitrate KNO3. Okay? That leaves us the barium and the chromate to come together. Well, it just so happens that barium is a +2 charge and chromate is a -2 charge. So we can say that we have BaCrO4. But now which one is our precipitate? Well, we have to go to our solubility rules. So here we can see that all potassium salts are soluble. So this allows us to indicate that the potassium sulfate, or the potassium nitrate, is going to be aqueous. When we take a look at the rest of the rules, we really don't see anything about chromate, but we kind of can see that barium tends to not be soluble in certain solutions. We also know, although barium is soluble here with hydroxide, so it's kind of like, how do we guess? How do we know which one it is? Well, we saw it with our own eyes. We know that there's a precipitate. And we also know, because of the solubility rules, that the potassium nitrate is always going to be soluble. That tells us then that the barium chromate is going to be precipitate. This is why we cared about physical states, okay? In our last set of book problems in Chapter 6, when we were simply balancing equations and writing balanced equations from the word descriptions. We need to know our physical states so that we can identify our precipitates with precipitation reactions. Now, the other thing that we can learn is something called net ionic equations. Students tend to not care for them so much, but they're really very simple. You literally take the two ions that come together to form the precipitate and you just write them as an equation, okay? So basically, net ionic equations involve only the ions producing the precipitate. We must balance these as well, okay? So let's take a look. We know that our barium ion was aqueous in solution initially, and it combined with our chromate ion also aqueous to produce our barium chromate precipitate. Now when we take a look here, everything has to be balanced. Well, we only have one barium ion and one barium ion, one chromate ion, one chromate ion. Our +2 and -2 charges cancel each other out on this side, so the reactant side has an overall 0 charge, and our precipitate also has an overall 0 charge. So this reaction is balanced. This is how you write net ionic equations. Here's a second example with a typical written description in a problem that you will encounter over break. Please write it down. Okay, so we are charged with predicting whether or not a reaction will occur. Here's the thing. If both products are soluble in solution, then both products are also aqueous. Technically, all we've done is create a mixture then, and that's not an actual chemical reaction. So we would write no reaction or no RXN. So let's take a look here. We have sodium carbonate. So sodium is a +1, carbonate is a -2, and this is going to be aqueous. And cupric sulfate, cupric is +2, sulfate is -2. We got to shrink that down a little bit here. And we have to decide if we do in fact have a chemical reaction here. Well, what's going to happen? This is obviously going to be a double replacement or double displacement reaction. So our sulfate ion is going to come and hook up with sodium, and our carbonate ion is going to come and hook up with the cupric ion. So let's write those down first, okay? So we know that the sodium ion and the sulfate ion are hooking up. Let me shrink that down. And we also know that the cupric and the carbonate are going to hook up. We also need to make sure that we balance this out. So go ahead and take a minute and balance this. Yep, it already is balanced. Okay, so now we are charged with figuring out if the reaction actually occurs. So we have to go to our solubility chart, okay? If you recall, all sodium salts are soluble, okay? So that looks kind of like the sodium sulfate is going to be soluble, okay? And all carbonate salts are insoluble. So that tells us that this cupric carbonate is probably going to be the precipitate. Now, all sulfate salts are also soluble. So we have the sodium ion and the sulfate ion being soluble. Sodium's not an exception to that rule. So we can obviously then confirm to ourselves that the sodium sulfate is going to remain in solution, and because carbonate salts are insoluble, that confirms to us that a reaction does in fact happen, and our cupric carbonate is going to be our solid. Okay, so the last thing we need to do is write the net ionic equation that shows the two ions that come together to form our precipitate. So we know that we have cupric, which is Cu plus 2, and originally it was aqueous because it was dissolved in solution, okay? And our carbonate ion is also aqueous, and they came together to form cupric carbonate precipitate. When we look at balancing, we only needed one of each ion to make the compound to balance out the charges, and on the reactant side the -2 and the +2 cancel out, so we're neutral overall here on the reactant side, and our compound is also neutral on the product side. So that is how we predict precipitation in our precipitation reactions. This is also how we write net ionic equations. Now you're going to do your book work and keep practicing. Make sure you also memorize those solubility rules. Have a great evening.